So today you'll be seeing a video on causes of failure in construction. We have 4 presenters speaking today. The first presenter will be Layla. She'll be speaking about inadequate soil tests. The second presenter will be James, speaking about bracing. The third presenter will be Jack, talking about the termite risk management. And the fourth presenter, Michael, will be talking about a project in Glen Waverley of a construction pit where a landslide has fallen through.
So I'll be talking to you about inadequate soil tests and the impact that it has on homes in Melbourne. Over the recent years, it has come to light the number of reports of failures in the construction of new residential building in Melbourne's north and western suburbs. There are a number of articles that cover this, but the one that we're concerned with for this presentation is written by Simon Johansson, entitled "Thousands of Suburban Home Owners Facing Financial Ruin," which was written on the 8th of June 2014 and published in The Age. Although an extreme title, it concisely sums up the problems being faced by many residents in the northern and western suburban developments. New homes of up to 10 years in age are starting to experience a phenomenon called slab heave. As you read through the article, it explains slab heave is where volatile soil movements under a home's foundation cause walls to crack, doors and windows to jam, and floors to tilt. It has highlighted this as a major problem and blames this on inadequate soil reports, suggesting that many thousands of new homeowners in the Wyndham, Melton and Hume local government areas are affected by volatile soil movements occurring under the home's foundation. This is causing the walls to crack, doors and windows to jam and floors to tilt in newly developed homes. So what is slab heave? Slab heave is when expansive clays, such as the ones found all over the Melbourne region, are exposed to moisture below the slab. This results in the clay swelling and expanding, pushing the centre of the slab upward. This deforms the slab and places strain on the internals of the building, causing the structure to shift and cracks to appear. So as you can see in the diagrams there, really it's just where water's pooling unevenly under the building, which is pushing up, in this case, with the expansive soils when there's too much water content, and putting pressure on the slab. Or in the reverse, once it's really dry, such as the drought that Melbourne faced for a very long time, then this soil will shrink and this will have the adverse effect on the slab. Australian Standard 2870 version 11 is the Australian standard that lays out the process and criteria for the classification of a site, as well as how to design and construct the footing system. So what is a site classification? It is interested in the composition of the soil profile and the expected amount of movement in the ground surface and the depth in which this movement extends. The guideline clearly outlines the process for identifying how to assess the site classification and then informing the user of what this means and what they would need to do next. So as you can see in the slide here, there is a number of different site classifications, starting at A, most sand and rock sites with little or no ground movement from moisture changes, through to E, which is extremely erective sites which may experience extreme ground movement from moisture changes. But even another site classification, P, which stands for problematic, which is the worst case scenario. Once the site classification has been established, the standards will then explain whether the footing system will need to be in reliance of Section 3, Standardised Footing Systems, or require an engineer to design footing system, which is outlined in Section 4. It's important to note that AS 2870 version 1996 was revised due to the end of a 14-year-long drought in Victoria, starting in 1995 through until 2009, resulting in our now standard AS 2870 2011 version. This drought had a significant impact on the soils and sub-design over this time, and when it ended caused a lot of shortfalls, shortcuts and oversights to become apparent. Any house built before 2011 would have been built to these previous standards, which may have been partway responsible for the issues arising in the new development more recently. The table to the side reflects Section 3 of the standards, which lays out how to design a footing system that does not require an engineered solution. So as you can see in this table, it goes through all the different site classifications, and then it suggests what type of construction you'll be doing, and then it gives you some information on what you actually need to do when designing the slab. Another article that was written more recently in November 2015 by Mark Whitby, entitled "Inadequate Soil Reports, Melbourne's Big Secret," looks at this phenomenon as well and attributes these issues to the soil report writers. This then leads to the structural engineers designing inadequate slabs for these sites, leading to an array of problems years after. He explained that obtaining the cheapest quotes for soil reports may have led to many of the report writers taking a quicker option and relying on clause 2.2.1b, which states site classifications based on a characteristic surface movement in accordance with clause 2.2.3, as opposed to consulting Appendix D, which may have been required in some of these situations. This resulted in classifications being downgraded, leading to underperforming slabs. Behaviour and Design of Residential Slabs on the Expansive Clays of Melbourne. A report produced in 1979 that looked into the behaviour and design of residential slabs on expansive clays in Melbourne. It identified the problem that Melbourne has when trying to build on these soils. I take a quote straight from the report, which says, "In the eastern states of Australia, the expansive nature of the clay soils and the prevailing climatic conditions lead to the development of significant seasonal soil movements in the top few metres of the soil. When light domestic structures are constructed on these clay soils, foundation failure of all but slabs with integral stiffening beams are relatively common." The Melbourne region soils are identified by their geological origin, being made up of clay soils that is divided into two groups. 1. The Quaternary basaltic clay, and 2. The Tertiary to Ordovician clays. Because of Melbourne's semi-arid climatic patterns, the clay soil profile sees seasonal soil moisture changes of up to a few metres in depth. As you can see in the image here on this slide, to the eastern suburbs of Melbourne really is subject to Quaternary basaltic clays, and the west is subject to Tertiary to Ordovician clays. This leads to cyclic volume changes and vertical movements throughout the year. This can be described as seasonal heave. When an impermeable cover, such as a slab, is poured onto this soil type, it will affect the moisture in the clay and will alter the soil moisture change pattern. The clay underneath the slab will be unable to release the moisture as freely as it is used to. This will lead to slab heave, which in turn puts strain on the structure of the building, leading to cracks and failures. As you can see in this image to the right here, it shows you different situations with moisture content under the slab. As clays absorb soil, they tend to expand, and as they dry out, they will shrink, and then you will have different defects in your slab depending on what's happening in the ground underneath. So what next? Soil classifications and reports should be completed to ensure a thorough knowledge of site characteristics have been obtained. But is the current standard practice for designing slabs appropriate? Do we need to purposely over-engineer slabs to mitigate future problems? Should everyone move out of Melbourne and we stop building on these expensive clay sites?
Now we'll be talking about bracing within the construction industry, and how that will lead to construction failures. Overview. When wind flows over a building, it applies a different pressure on a flat vertical wall to that of a sloping roof or surface. The Building Codes of Australia have set tables that show the nominal bracing that is necessary to keep a building standing. The tables need to know the ratio between how much roof area the wind sees as opposed to how much wall area the wind sees. The building width and roof pitch establish this ratio. Area of elevation. To work out the nominal wind bracing, you must work out the area of elevation, or the area that will be affected by the wind. Except for simple L, H or U shapes, where each part of the building has an identical width and pitch or contains no vertical surface on the roof area such as a gable or skillion. Each of the parts must be considered individually and not added together. Bracing should be distributed throughout the house approximately in proportion to the forces relevant to each shape. If a veranda or the like is presented to be enclosed, it should be included in the area of elevation calculation. A veranda should be considered enclosed if any part of the main building projects out into the veranda or an end is filled in with lattice or similar. Once the area of the house has been identified, it is time to work out the racking force necessary. Below, you will see an image of a roof area of elevation and a wall area of elevation. These are the two areas that you'll be calculating to get your racking force. Once the area of elevation has been met, racking force is the next component to work out. The total racking force in kilonewtons shall be calculated as follows. Project area of elevation, meters squared, times lateral wind pressure, kilopascals, equals total racking force. The image below shows how racking force pushes a building across, and our uplift brings over the top of the building and brings the wind upwards. Wall bracing. Walls shall be permanently braced to resist horizontal racking forces applied to the building. Wall bracing shall be designed to resist racking forces equal to or greater than the forces calculated from racking force. The total capacity of bracing walls shall be the sum of the bracing capacity of structural bracing walls. Below you will see an image of how a wall is braced with ply sheets. This shows detailed information about the distances between the sheets, anchor points, and the wind load. Temporary bracing. Australian Standards 1684 only requires temporary bracing to be 60% of the permanent bracing, and this reflects to the lower probability of a building being subject to its long-term maximum design gust wind speed event during the relevant short period of construction. Below you will see an image of the temporary bracing coming off at a 45 degree from the top plate all the way down to the bottom concrete. This will be dynabolted. This will have a timber dynabolted straight into the ground and then timber nailed on straight to that. In conclusion to bracing, nominal bracing must be met through Australian standards, while temporary bracing of the building must be met 60% of the nominal bracing required. Otherwise, a failure in the construction will occur and the building has extreme chances of falling over. Below you will see two images of obvious construction sites that have not had enough bracing and have fallen over. The first one on the left-hand side, that is from out in the west of Victoria, and where it is a lot flatter plains, and obviously the wind's picked up, and the builder has not braced that building enough.
So this part of the case study, I'm going to focus on the effects and problems caused to a building from termite damage. Termites, they're also referred to as white ants. They serve an important function in nature by feeding off dead trees and converting them into organic matter. Unfortunately, the timber we use in constructions such as subfloor, wall, roof framing, pergolas and decks are equally as appetising to some of these insects. There are many hundreds of termite species in Australia, and about 20 of these can eat through the solid timber in buildings, causing serious damage and expense. They require an ideal temperature and humidity levels to survive. They live in colonies of hundreds of thousands, sometimes 7 metres below the soil surface, and have extensive tunnel networks that can extend up to 100 metres from the nest. So this is a close-up image of what they look like. Problems that they cause. Termites thrive on moisture, making buildings settled in the damp, humid southern states a prime target for these pests. They can cause extreme amounts of structural damage to the home, creating safety and cost problems. As well as the structural timber in the building, termites can also damage plasterboard, carpets and fit-out timber. All new houses, including extensions built within areas designated by councils to be subjected to termite infestation, must have some form of management against termite attack. This is a requirement of the Building Regulations 2006. It also means all new buildings and extensions need to abide by Australian Standard 3660. This is the extent of damage they can create to structural members. This is a roof truss, so you can picture the amount of damage this would create if any load was applied to it. Prevention techniques. Smart building design helps to minimise the risk of termite damage. Strategies include reducing the amount of timber used in buildings, designing the concrete slab with edges exposed for inspection for termite activity, laying timber floors with underfloor inspection access points, consider open or at least well ventilated subfloor areas, ensure good inspection access and crawl space under the house, provide good surface drainage to keep the subfloor area dry. It also includes use of treated timber framing to minimise the materials at risk, not to build right up to the boundary, Inspections may not be possible from the neighbouring property, therefore increasing the risk of hidden attack. Metal stirrups should be used for setting pergola, gate and veranda posts into the ground. Proposed extensions or alterations to the building must not result in the removal of existing termite barriers or access for inspections. Plumbing leaks, drainage problems and roof leaks should all be dealt with quickly, as damp conditions attract termites. However, the main types of prevention are physical barriers and chemical barriers. So physical barriers include ant caps, stainless steel mesh, granite chip barriers and termite sheet under slab and around pipe penetrations. And your chemical barriers include a chemical termite barrier involves applying a liquid chemical to the soil, either under concrete flooring and or around the entire perimeter of the building's foundations. There are various types of chemical termite barriers. For example, some chemicals are designed to kill the termites and others are designed to deter them. Some barriers will require ongoing inspections, maintenance and or chemical replenishment. So this is an image of a termite nest hidden in the wall cavity. There are a number of ways they can get into there. They can even get through cracks in the slab up to 1.5 millimeters wide. So to sum up, prior to building, consult your local council to determine whether the area in which you are planning to build has been declared subject to termite infestation. Choose a termite management system to suit the specific needs for the type of construction, and understand the system of termite management and maintenance requirements for the building.
Glen Waverley Construction Pit landslide presentation. Today I'll be talking about what happened, why it happened, and the procedures to rectify it. The case study. Back in July 2015, a site planned for a $5.5 million medical childcare facility at 170 Highbury Road, Glen Waverley, was excavated without following correct building practice. It caused the soil around the perimeter of the site to slide, which was as well holding the foundations of the neighbouring properties. Here are a couple of photos of the site. The photos show the two properties that it currently affects. It also shows the properties hanging over the edge and the soil that has caved away and is sitting at the bottom of the pit. What they did wrong. The incorrect building process was conducted. There was no regard for the surrounding infrastructure by the builder or the building surveyor or the contractors who did the work. There was no boreholing done. There was no concrete piling done along the perimeters. There was no shoring done anywhere along the site, and there were no concrete wall linings done to complete the job. What is boreholing in construction? A borehole is a narrow shaft dug into the ground, either horizontally or vertically, to either assess the soil levels for its classification or to start the process of underground foundations with the use of concrete piling to follow. Here are two photos of what is boreholing. One actually shows you the hole which has been dug, and the second one actually shows you the machine of how it is constructed. Well, not when I say constructed, how it is performed. In the next case, there was no concrete piling done. So what is concrete piling? Concrete piling is used in deep foundations, which is a type of foundation which transfers building loads from the earth's surface to subsurface levels. It is also used on the boundary of the site to excavation to eliminate the event of landslides once soil is removed. Here are two images, one showing the cartoon drawing version of what actually happens with concrete piling and how the machine conducts that, and two, the other photo shows you a more real life photo of how it is how concrete piles are put into the ground. These also can be done with the use of reinforced bars which can go down through the ground, But these, in this photo, have shown precast concrete piles which can be put in. But as mentioned, you can use reinforcement and actually pour the concrete into the holes yourself. What is shoring? Shoring is the process of supporting a building, structure, or trench with shores, props, when in danger of collapse or during repairs or alterations. Shoring comes from shore, a timber or metal prop. Shoring may be vertical, angled, or horizontal. Here are 3 photos showing you what shoring is about. One shows you the in-trench form. One shows you it supporting the sides of an excavation when the excavation has already been done. The other one shows the actual bars which are on an angle going back into the excavation area, which shows the different process. Shoring can be done in many processes and different styles, but all follow the same rules and guidelines. The recommendations for this site: if the correct engineering practice was conducted with the use of concrete piles, then shoring the sides, then complete with concrete wall linings, the issue of the Glen Waverley site would not have occurred. What they did do is they filled the hole back in with about 1,000 truckloads worth of soil and have now left the site empty. It will now be some time before any work can be done, as that soil put back into the hole needs to settle.
Thank you for listening and watching our video. We really hope, on behalf of all 4 of us, that we have given you an overview of causes of failure in construction and a simple understanding of 4 different elements that could lead to causes of failure. Thank you.